Hello again. This is Math 2233 coming to you from the College of DuPage. The title of this lecture is Computing Double Integrals over More Complicated Regions. And you always want to be an active learner when you watch these videos. For single integrals, the region over which we integrate is always an interval. But for double integrals, we want to be able to integrate a function, lowercase f, not just over rectangles, as we did with the iterated integrals in a previous lecture, but also regions D of a more general shape. And let's just think about the general shape as being a bean-shaped region like that D. And there are topological characteristics that we'll talk about later, especially when we talk about Green's function. But for right now, just think of it as being this. And we do suppose that D is a bounded region, which means that D, this bean-shaped region, can be enclosed in a rectangular region R. And so, since this is bounded, we can build a rectangle that goes around it, and that is the capital R. Then we're going to define a new function, which is capital F, with domain R now defined on the rectangle, and we define capital F of xy to be lowercase f of xy if xy is in D, and being 0 if xy is in R but not in D. Now I want to emphasize that this is still a volume. If you think about what we're doing, it's going to be a volume. But now what we've done is the double integral over D of f of xy dA then is equal to, because of the definition of capital F, it is the double integral of capital F of xy over the rectangle R dA. And the reason we've done this is a very important technique in mathematics, because we know how to compute this, and we're using this definition of how to compute this in order to come up with a way to compute this. Now, we're not going to do this in general regions. We'll continue to expand the type regions that we can do, but for right now we're going to talk about a plane region. D is said to be of type 1, that's a Roman 1, like an I, if it lies between the graphs of two continuous functions of x. That is, the domain looks like this. X runs between A and B, but Y runs between G1 and G2 of x, where G1 and G2 are continuous on AB, and we can look at some pictures here. So these are examples of type 1 region. You see you run from A to B, but the top and bottom are curvy. You run from A to B, but the top and bottom are curvy. You run from A to B, but the top and bottom are curvy. So type 1 really means only funky on the top or bottom, and or bottom, but numerically are just limits for x otherwise. So in order to evaluate the double integral over D lowercase f of x dA, where D is a region of type 1, we choose a rectangle, and we'll just take the rectangle here to be x runs from A to B, and y runs from C to D, that contains D. And we let capital F be the function that was 1 only when, or that is equal to f of x, lowercase f of xy, only when we're in D. So that's the capital F. So then what we have is this integral is equal to this integral, but then that's the integral from A to B and C to D of capital F of x dy dx. But now here is where some of the magic happens. You see, now when we're doing this, we're integrating dx last, so we're integrating y first. Well, think what happens. As you go from C to D, it's 0 till you hit this boundary. And then you have capital F of xy for all of these points, and then it becomes 0 again. So you see this integral, when I'm drawing this for fixed x, this is fixed x, that's what that means. For fixed value of x, the y runs from G1 of x, the bottom, to G2 of x, the top. So this is an important thing because this is what we're going to be computing. It is important to draw a picture, and it's important to draw this line, I think. We can also consider plane regions of type Roman number 2, which can be expressed this way, where y runs between c and d, but x runs between continuous functions h1 of y and h2 of y, where h1 and h2 are continuous. And so here's an example of those regions. So you see y goes from c to d, but x on the left and right are continuous functions, but they can be very curvy. So type 2 means you're funky on the left and or on the right, but it's nicer on the top and bottom. And here, what we're going to do is we're going to integrate second with respect to y going from c to d, but when we draw the fixed line here, what will happen is that x will go from h1 of y to h2 of y. You want to think about what's going on here. You don't have to memorize which one is type 1 or type 2, but you have to know how do you approach the problems when we're trying to solve them. So let's do a problem. So you want to evaluate over the region D, x plus 2y dA, where D is the region bounded by the parabolas y equal 2x squared and y equal 1 plus x squared. You know what to do. Let's see how you did. Now, it's very important in solving these problems that you graph them. And I will ask you on tests to do problems that are very similar to this one. So you need to graph it first of all. So down here, what I do is I graph this region D. And also I find the points where these curves intersect. So this is -1, 2, and this is 1, 2. So I graph them and I find their points of intersection. Now, since the lower boundary is, and the lower one is y equal 2x squared, and the upper one is y equal 1 plus x squared, what I do is I say, well, I'm going to integrate with respect to x second. So I'm fixing x, and I'm saying y runs from 2x squared up to 1 plus x squared. So that's what's happening here. So you see dx is second. I'm integrating with respect to y first. I'm integrating the integrand from y going from 2x squared to 1 plus x squared. And then I evaluate this as an iterated integral. So what I'm going to do is I do the integral inside first with respect to y, treating x as a constant. When I do that, I get, as my antiderivative, xy plus y squared. And I have to evaluate this using the fundamental theorem of calculus, a top limit of 1 plus x squared and a bottom limit of 2x squared. So I leave this integral from -1 to 1 here and the dx here, so those are still here, but then I plug these in and simplify and see what I get. So I plug in the top limit here for y, so everywhere I see a y, I am substituting 1 plus x squared. And I subtract by the fundamental theorem of calculus, and everywhere I see a y, I plug in 2x squared, getting this. Make sure you follow this calculation. Then I simplify this. There's algebra always involved. And I simplify it this. I have an expression in x. And now I integrate dx from -1 to 1. I use my techniques of integration, and I'm getting -3. That's x to the 5th over 5 minus x to the 4th over 4 plus, I factor out the 2, that's x cubed over 3. This is going to be x squared over 2 plus x. I evaluate that at 1 and -1. I do expect you to be able to do these calculations, and yes, my friends, there will be fractions. And so you see, what we get for this answer is 32 over 15. Now note, when we set up the double integral, it's essential that you draw a diagram. And it's helpful, and I would almost say essential, that you draw a vertical arrow to help you with the limits of integration. Then the limits of integration for the inner integral can be read from the diagram, from the lower boundary to the upper boundary. And for type 2, the arrow is drawn horizontally from the left to right boundary, and you can read it off your drawing again. Let's look at another problem. So here I'm asking you to find the volume of the solid that lies underneath this paraboloid z equal x squared plus y squared and above the region D in the xy plane bounded by the lines y equal 2x and the parabola y equal x squared. You know what to do. And we'll see how you did when we pick up with this continuation of this video. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all, and I will see you in the conclusion of this lecture video.